Hi, Shashank. Can you hear me?
Hello, sir. Yeah, you're audible. Just making you as the co-host. Yeah.
Okay.
So, Professor Vandana will be joining to introduce you to the students,
Okay.
and maybe by 6:05 or 6:10, if all the students join, we can start off.
Sure, Shashank. Thank
Yeah.
you so much.
Thank you.
Good evening, sir. Am I audible?
Yes, ma'am, you are audible. Please go ahead.
Yeah, we'll just like wait for another 5 to 7 minutes, sir.
Sure, no
Yeah,
problem, ma'am.
thank you. Okay. Good evening, sir. I think we can probably start. Good evening, everyone. Good evening, Dr. Nandish. I am Professor Vandana. I'm from the School of Basic Sciences, the Department of AIML and Cybersecurity. So, a warm welcome to you and all the students this week. And in this week's Industry Connect session, we have with us Dr. Nandish, who is the global leader in the measurement sciences. He is also an expert in predictive data modeling. Today, he's here with us to talk about deep learning model optimization and tuning the network. Sir, may I hand over the session to you, sir?
Thank you, ma'am. Okay, without wasting any more time, we'll get started. So meanwhile, for the benefit of internet bandwidth, I'm switching off the video and we'll go ahead with the today's topic, which is tuning the deep neural network. This includes, we will learn what is deep neural network and how to tune, or I will show you different ways of tuning the deep neural network for getting the desired results or making a better prediction in terms of both accuracy as well as efficiency. So in next 42 minutes or so, what is that I want to accomplish in this session, and you can do the co-learning as well. When I say you, all the students who have participated in this session. So one, we will learn different ways of tuning the deep neural network. Second, we will go through one of the real-time case with the image processing and the prediction, how we can tune the face recognition. The third, I will show you through the Google Colab, one of the data set, and how best we can tune to make sure that what are the different ways of tuning the deep neural network to make the accuracy and the efficiency what we want to achieve. So with that agenda, I will try to keep slides minimum and the other activities around the lab and the Google Teachable Machines more. So let's start that. First, we want to understand what is deep neural network, right? So in a simple layman terms, I will explain you. The artificial neural network is set up with a network of perceptrons. Perceptrons are nothing but the nodes here. For example, X1 is a node. Let's call this as Y1, Y2, Y3, and this is Z1. So X1 here is one of the node in the input layer. If we have to call any network as a artificial neural network, then it has to have at least 3 layers. One input layer, the middle one is called as hidden layer or dense layer, and the third one is output layer. So if our hidden or dense layer is 3 or more number of layers, then that neural network becomes a deep neural network. So what does this means is that the complexity in solving any of the problem becomes more complex, and with the deep technology and deep neural network, we will be able to solve some of the complex problems like clear image recognition or prediction in certain way that we are beyond the ANN network. All that is possible. So that becomes possible with the deep neural network. Okay. So how does this deep neural network is set up is, it is set up, as I said, with the layer of perceptrons, which are nothing but nodes, and nodes, each nodes depict in each of the layer. Okay. And each of the node is connected to the another node, which is called by here Y1, and it is called as a dense. And each of that node is connected by different weights, let's say W1, and with different biases, let's say B1. And both of this is run by a active function, let's say F. Okay. So function of W1 is equal to B1, including biases and weights. So this is how each of the network is connected. So how this neural network will help us in terms of doing any problem solving or prediction is, once you give the input in terms of data points or a data set or an image, for that matter, if you're solving an image recognition or a face recognition as a problem, it will work as an output for one of the hidden layer. And once this works with active function, weight, and biases, this will become an input to further dense layer or a hidden layer, which will be called as active function 2 with the weight 2 and the bias 2. Like that, it will work with each of the layer and it will give output. So once this goes through 3 dense layers, the output function Z is equal to the combination of F1 W1 plus B1 plus F1 W2 plus B2 plus F3 W3 plus B3. So all put together, the output what you get, that will be your output layer, which will be in the form of a Z. So this is what, in a glimpse, in a short theoretical way, I have explained the deep neural network. So now I will not spend time in explaining all that. So I have covered what are nodes. Each of this is called as node. Okay. So we, as a moderator of a neural network, we can always moderate these number of nodes, these number of layers, as well as the output Z function. Okay. So since we have control on managing the deep neural network, we can define or we can improve the prediction output as well. Okay. So what are the ways how we can tune the deep neural network are? There are 2 ways. One, we can look at weights and biases, which is W1 and B1. which are called as parameters, and in ANN algorithm it is called as params or parameters. These are normal parameters. But today we are going to learn how to tune the hyperparameters. So this is something which will help you to achieve greater accuracy. W1, W2 can be achieved easily through the dataset management, but hyperparameters tuning will help you in achieving greater accuracy at very flexible memory or CPU or GPU usage and all that. Okay, so now we have to understand what are these hyperparameters. Hyperparameters in this deep neural network is number of layers is one of the hyperparameter, nodes, number of nodes in each layer, and the active function. So these are some of the hyperparameters. At the same time, there is something called cost function, or we call it as loss function. Okay, what does this loss function does is it will calculate the infrastructure and the memory and the GPU usage for running that particular algorithm through that deep neural network. So that function has to be minimum as possible. And each of the deep neural network will consume some of the cost function or loss function, but that has to be minimum. That is where we will achieve the model optimization. Then learning rate is the rate at which the deep neural network is learning on its own. Normally, the deep neural network learning rate will be always, or most of the time, it will be 0.01. Okay, that will be the normal. And in terms of optimizers, there are different set of optimizers. For example, there is something called stochastic gradient descent as one of the optimizer. Then there is something called Adam optimizer. There is something called sigmoid, and also there is something called softmax. These are different. You guys are with me? These are different optimizers. Okay, you guys are with me, right? I've not lost you guys. Okay.
Yes, sir, we can hear you.
Okay, so I said stochastic grade descent. There is something called Adam optimizer, and also there are something called softmax as optimizers. Those are some of the optimizers, and there is easy way of doing using batch size and epoch. Okay, I will explain each in detail. Epoch is nothing but your data set will go through the deep neural network at least once while training. That is called one epoch. Okay. And normally, by moderating the epochs, we can always tune the deep neural network. And batch size is the number of set of data points which will make through one training is called as batch size. And normally, we don't touch or moderate the batch size because batch size is always linked with the platform which you are using. For example, if you are using Google platform, then Google as a company will manage the memory size required for it. So we will not taper with the cost involved in that. If most of the enterprises use Microsoft Azure or AWS, which will be managed by pay as you use. So it will not be a problem to manage as a batch size. But yes, epoch is something which you can manage. Okay. So we'll do one thing. We'll create one deep neural network real time, and we will try to understand how to tune it. So I will show you how to manage using the batch size and epoch. The other things also we will learn in next 40 minutes or so. Okay. So let me open up Google Teachable Machines. Okay, here is the link, and we'll get started. So here, I will not use any of the data set for now because I want to show you some real time. We'll use image. Okay, here we'll create one happy. We'll create one deep real-time network using real-time data sample. Okay, so I will create three classes here. Happy class, where my face is happy, then neutral, and then sad. Then we'll try to predict the sentiment of my face detection, and then we'll tune it. So that is what we will learn and do it now. So let's create a happy face sample. So hold for recording. Okay, so we have created around 200 images, which is more than sufficient. Now we will create one neutral face. Okay, so we have created. We will add one more, which is sad face. Help us in detecting that. Assuming that this is the maximum sadness I could show. Okay, so here we have created three classes here: happy face, neutral, and sad. Okay, so with this, I'm going to train the artificial neural network here, and then I will show you how to tune this. Okay, so I will press on training here. Okay, so it is preparing to train. So overall 200 each, overall 600 images will get trained here, and it will not take much time. Okay, so during that time, meanwhile, it trains. So here it is training. So here I will tell you for the images which I have done here, overall 600 images around. So epochs it is using is 50. 50 is the epoch. See, it has done the prediction. If I'm happy, see, it is 100%. Then neutral. Then if I'm sad. So on the sad prediction, accuracy is not that good. So we can further improvise. So to achieve this, if you see here, the prediction, it is using epochs as 50. Epochs in the sense, I will explain you again. So one epoch means each of the every sample is training the data set through this at least once. Means my each of the image here will go, means all 600 images will go through it once. That is one epoch. So to get an output prediction of this, it is taking at least 50 epochs. Okay, this is what, to the best memory available in the Google at this point in time, it has done it. And batch size is, for every time it will take 60 images and process it through this artificial neural network. Okay, as I said, learning rate is 0.01. Okay, so we'll understand what happens at the underroot in the sense what happens at the backend. See, in this backend, we will understand that what is the accuracy we are calculating here in my own samples of face detection, sentiment analysis using the face detection using deep neural network. So happy accuracy is 100%, neutral is 100%, sad is 100%. Okay, this is not a great samples because I failed to create different expressions out of it. Ideally, if we see this 100%, then this is something overfitting. So I failed to create such differentiated face expressions, but we can try anything with a dog or a cat or a pet or a kid who can make more faces. But however, we'll continue to tune this better. And there is something called confusion matrix. This confusion matrix is a 3x3 here because we created three classes here: happy, neutral, and sad. So this output is because of the logistic regression. So if you see here, the accuracy per epoch, 80 to 100% it is achieved because it is overfitting here. And a loss function or the cost function, which I said here, it has done really well and it has come to 50 epochs here. So what we will do is we will tune this to achieve better accuracy. Actually, 100% is a very good accuracy. I don't know how much better we can do, but definitely I will show you if we reduce the epoch, what it will do. So let's keep epoch size to 20. Then again, train this. You will see how accuracy per epoch and loss function is changing. See, so what does this mean is, in a real time, the algorithm is self-learning and achieving the better accuracy and the loss function. See, with this 20 epochs, before it was 50. So I made a number of epochs less. So now instead of 80%, it has come down to 75 and it has done the accuracy at 100%. Same as loss function. So what does this mean is, let's go to the accuracy prediction, how we are. Okay, so here with this reduction in the epochs, we achieved a realistic sentiment of SAD at 97%. In the sense, when my face is sad, for example, so the images of sad are not so accurate. If I'm happy, it's easily detects at 100%. If I'm neutral, my face is fluctuating. This is real time. Okay, and this is something at real time. You can do it with image capturing and tuning the network. Here we have tuned only the epochs and the batch sizes. Batch sizes also you can do it, but normally this batches will be at 16, 32, 64. This is because Google has given us the memory to process it. If you make more, then obviously the time taken to learn that will be higher. Okay, so normally we don't disturb the batch sizes to improve accuracy, but yes, epochs can be modified or moderated to achieve better accuracy. And exporting the model is very easy. You can download this or contribute, or yeah, see here, you can download it easily. Download my model. So easily your model will come down and you can use it in any other platform. So this is one example which I wanted to show you today. Okay. So coming back to my PPT. So here, what we learned now is just by using the epochs, okay, face detections can be made better, or tuning can be made better in the face detection. So that is one real time I showed you. So now there are other methods also which I will take you through. So how the training process can be set up is using the training data set. Okay, so here I will take iris data set. What is iris data set means? Iris is a type of flower. Okay, it has got three types of flower like varicosa, setosa, and there is one more data. Let me take up the data set first, then it will be easy for you guys to understand. So here, this is iris data set. This you can find it anywhere else. So using this iris data set, we will try to tune the length of the leaf or a petal, and then we will make the classification of that or prediction of the type of flower what it has. Okay, so here this is the data set of 150 data points with 1, 2, 3, 4, 5 variables, in which first 4 are input nodes, and the fifth one, which is species, is a output function, which is Z, which I showed you in the beginning of the session. Okay, so first one is sepal length, sepal width, petal length, petal width. So with these 4 variables, we are going to predict whether it is a setosa kind of a flower, or versicolor, or vernica. So these are the 3 type of flowers which we will make the detection. Okay, so to do that, let's understand that how to set up the tuning process. So first take the data set, which is iris data set here, of 4 input layers, and fifth one, which is will be your output layer. Okay, create a network with an intuition. Start with random variables. Normally weight and biases, we keep it random because we want neural network to run or learn on its own on the first phase. So we try to keep weights and biases, which is weight W1 and bias B1, as random as possible. Then minimize the error, which is my loss function. Okay, and also adjust the weights and bias until the loss function or errors are minimized. Okay, that is where we have to keep setting the epochs and other things. Then improve the model, adjusting the layers, node counts, and also hyperparameters. Hyperparameters are some of the optimizers. All these are hyperparameters. So now, how to set up the model optimization and tuning? We can do it in 2 ways. One, optimizing through inference, and the other one is optimizing through training. Okay, so these are the 2 methods of optimizing any deep neural network. So now coming to how to optimize for inference is by achieving the better accuracy. The better accuracy in the sense, better Z value. Z value will lead a better F1 score. What is F1 score? In any of the prediction model, you take anything, random forest or logistic regression or any support vector machines. You take any of the prediction, F1 score will tell us the combination of precision and recall. So to get the best combination of precision and recall, the F1 score above 90% is always advisable. So that we can achieve, but we can achieve at what cost? That is what we have to lower the cost by having the model size smaller, by having the minimal inference latency, and also using less of memory space what is required. So we have to always have a balance between accuracy and cost. We can achieve the accuracy, but not at a maximum cost. Then it will become a overfit model. So we have to always look at 95. If it is, for example, I did a face detection, right? It was showing almost 100% accuracy for the happy and neutral face. That is, some images are so good because it was taken very fresh and in front of the laptop now. So we were able to overfit it. We should never do that. Our face expression has to be different and captured. And that, like for example, I trained with 200 images of happy face, right? So this 200 images were enough for the Google machine to train my best happy face. I could have made a different or a better happy face to give them the 201th image to measure and predict. But my face expression was not that different that it was overfitting. So it should not happen normally. So if we achieve 95% accuracy at a minimum loss function, then we have trained the model to the best possible. This is one of the optimization which we do for inference. The other one which we do is optimizing for the training. In the sense, we will train this deep neural network in such a way that if the new image comes similar to that, the model should, or the algorithm should be automatically able to predict or make the image or identify the image and give the output. So that is what we will do the optimization for training. So how to do that? Time to train is lower number of iterations and number of experiments. We cannot keep changing the epochs to a level wherein it takes all day to do those epoch identification. So in 1 to 2 or 3 iterations, we should be in a position to find what is my minimum, what is my maximum, what is my average. When I look into average accuracy, then we will be having an idea of fair 16 is the number of epochs which we can have to have the maximum optimization of this training. And also there's something called training pitfalls. I will tell you one by one. Vanishing gradient is one of the training pitfall, wherein when you have your input x1 and it will go to the y1, then from y1 to y2, it should always give a relation, and y1 output should become an input to the y2. But if this doesn't happen, then that kind of problem or a pitfall is called as vanishing gradient. What is vanishing gradient? In the sense, from the input, it will go to the hidden layer, but within the hidden layer, it doesn't give any learning for the neural network. So that is called as vanishing gradient. Now there will be opposite also. Sometimes you will give an input in x1 and it will go to the y1, but it will explode to the y2. It will give so much learning that y2 alone, one node cannot handle it. It has to be segregated for different nodes. Okay, from each of the learning should not explode to only one node. That also we have to make sure. So that kind of problem is called as exploding gradient. So that's why, so during that time, if it explodes, then we have to create, let's say this is node 1 or layer 1, layer 2, then we have to create more layers, L4, L5, L6. So after doing this, then our explode gradient can be taken care. So that's how we have to manage it. Then overfitting in the sense your input layers only are more. So that has to be reduced, or you have to create outputs more than that or similar to that. Then your overfitting can be handled. There are many ways of handling overfitting. For example, you can make a dropout sample wherein you train only 30% and test 70%. But most of the time you follow 70-30, where we train 70% and do the 30%. But you can have a hold off sample, in the sense, let's say 50% of the sample. Let's say you have 200 images, like mine face detection. In that, you will use only 100 images and train the model. Okay, once the algorithm achieves accuracy of 95%, then you can have another 100 sample of images and then do the deep neural network. So that's how you can handle the overfitting. So now let's go to Google Colab. Okay, so we will do one real time with the data set. So I will go to Google Colab. Okay, so normally I use Jupyter Notebook, but here since we are using Keras as a function, that is well supported in Google Colab. So Jupyter we have to install and all that, so it will take time. And also all dictionaries supporting this is not available, so we will use Colab for our learning purpose. So I am in the Google Colab, and we will upload one of the file which is on tuning network, tuning the neural network. Let me upload it here. So here I can leave this.
Guys, please just stay put on the call. We'll wait until he joins us back.
Sorry, friends, there was a network interruption. So I will share my screen. Okay. So I was talking about, let's go to Google Colab. Okay. Go to Google Colab, click here and upload one of the file which I created. Okay. Okay. So here is the tuning of the deep neural network. So we will install few of the functions here like pandas, TensorFlow, Keras, sklearn, and matplotlib. Before that, I need to bring iris dataset into this. So let's bring this iris dataset into. Okay. So let me run this for our understanding. Okay, so here I'm using Google Colab and I'm installing all that what is required to measure the length of the iris flower for the better prediction. Okay, so let this complete so that it will help me. Before that, I will explain you the next set of things. So here we will initialize the iris data set into the deep neural network. So I will use pandas and also OS, NumPy, and also I'm using TensorFlow here using the Keras, and I'm doing entire pre-processing of that using standard scalar. Okay, so I will use the training and test split and do that in terms of giving a numeric value for each of the variety of iris flower what we have. So after that, I will import the data, read the file, and then I will create some of the hyperparameters tuning. For example, hidden layer or dense layer, I'm using 32 to 64, not the 16 one. And hidden activation, I have used ReLU, which is rectified linear unit. It is one of the prediction method. And used output node as 3. And I have used the optimizer as softmax. And weights and initializers of biases are random. And then optimizer here, I'm used root mean square propagation, which is one of the optimizer method. And then like that, I have set the epoch size to 610 and batch size to 16. Like that, I have used categorical cross entropy. Once you do this, once you run this, once this is done, yes, this initialization is done. Now I will initialize this. Okay, once you do this, you have set up the file for it, then you run the function. Once this is run, then I will show you how epochs and batch sizes which I showed on the Google Teachable Machines to be initialized here. It is very simple formula which I have run here. So what I have done is I have called the measure batch size and I have given a batch size as 16, 128 and 16. In the sense 16 as input, dense layer as 3 layers and then 16 as output. So similarly, once you do that, you will get a batch size of 16 here and then batch size of 32 and again the other one. So all that looks fine here. And then I will run the plot. There is an interruption here. So let's see. The layer has run that. Iris data set is here. Once you preparing the node, it will give you output like this. This is tuning the epoch. I have used the same accuracy measure here, 16, 128, 16. And then I have run the plot graph comparing the batch size epochs. So here, the blue color, which is batch of 16, is giving me the best accuracy. So what does this mean? I will keep the epoch in the Google Teachable Machine to 16, which is my best optimized accuracy. So what does this say is, by comparing the batch sizes, I have got a batch size of 16, which is to be optimum. So that will give me an indication that among all this data set, if I keep a batch size of 16, that is the most viable tuning method to use this iris data set. So let's see what is the output which I have got. Okay. See, the best size is, which is 16 here, has come as output here. So that means that out of the iris data set, the batch size of 16 is the best way of tuning it. So now let's understand what are the other ways of tuning. So let's try to learn that by increasing the number of layers or modifying the number of layers. So when I modify the layer, let's understand what is the best number of layers what we can have. So I will use the same thing. What I will do is I will give the same accuracy and I will give 1 to 6 layers. It can be in the range of 1 to 6 layers. Let's understand how this will come up to comparing the hidden layers. So this is how our deep neural network will function. So here layer 1 to layer 5, 1 to 6 layers we have given. And the best accuracy which I am getting is the blue one, which is layer 1. So at layer 1 only, since the iris dataset is so good dataset, we are going to achieve in layer 1 only. So we don't have to worry on creating multiple layers for this, which can save us the GPU time what is required for that. Okay. And there are other things like by moderating the number of nodes. If you remember, first slide which I showed you, here in this artificial neural network, there are different ways of tuning the network. So one, the number of layers what you create. For example, here there are L1, L2, L3, 3 layers of hidden layers. So this you can moderate and tune it. And you can have this node N1, N2, N3, like that, N4. Like that, there will be like N45 and N60. So these now nodes also you can plan it to reduce it. By reducing this node, what will happen is you can save the memory and you can increase the time of training, and also you can save the GPU cost. Okay, so graphic processing unit cost can be saved and it will reduce the loss function. That also you can do it. So let's see which is the best thing to do here on our data set. So let's nodes in the layer. Let me run this for you. And the formulas and the programming is very simple. I will call it as a layer list and I will give the input 8048. And then hidden layers, that's what we have understood, that with this iris dataset, 1 layer is enough. And with that, how many nodes are required? Let's learn that. So meanwhile, while that comes, I'll tell you the comparing the node 8. The best accuracy has come for node 32 here, which is the red line. Including the input and the output and the dense layer, if you can create it, that will be the best tuned and the optimized node for your deep neural network for the given iris data set, which has got 150 samples. Okay, so this is one of the comparison of nodes. Similarly, I spoke about the active function, right? How to choose the active function. Here we are talking about the 3 active functions. One is ReLU, rectified linear unit, stochastic graphic gradient descendant, and there is another called TAN-H, which is on the typical hyperbolic way of tuning the active function. So among these 3, we have done the comparison. And among these 3, the one which is giving the best result is the active function, which will give us the best solution for this iris data set. And similarly, there is the worst, which is not so useful in this iris data set, is the sigmoid function, which is on the stochastic weight data. Okay. And similarly, I've done the comparison of weight initialization, like based on the normal random, what are the different weights. So here, if you look at which has given the best comparison is the model random normal. That's why I told normally we don't tamper with the weights and biases, because based on the memory and the data set, the algorithm itself will design, and that will be based on the random normal. So that is the most preferred. Then yes, these are different ways of tuning or hyper tuning your algorithm to make sure that your output prediction is accurate. Okay, so with this two practical example, we'll look at what are the things to do and not do in the model optimization. So I spoke about optimizing for inference. I spoke about optimizing for training. Then the entire tuning process, I will tell you. For tuning any deep neural network, you have to set very clear goal. What is that you want to achieve? Let's say you have to say that I want to achieve 94% accuracy at minimum loss function. Okay, that should be your goal in any kind of tuning the deep neural network. You cannot have a target of achieving 100%, because if you assume that you want to have 100%, then obviously the efficiency will go for a toss and your model is going to go for an overfit. So always have anything between 85 to 95 as your target accuracy with the given minimum loss function. Then prepare your training data. Training data, I would say 70% you do it for training and 30% you do it for testing purpose. In case of then hold off the 50% training, or the other case you have to increase the sample size to achieve the better prediction. Then plan the model testing. So I will always say that don't go or settle for one. For example, if say you use grade descent as a model, then go for ReLU or do a comparison first asset and then settle at what is the best optimizer the deep neural network into a prediction model. So don't settle for one, but always have multiple scenarios and then optimizer to use. Okay. This can be in many ways, like by using Colab, GitHub, or even Google Teachable Machines for your practical usage purpose. Then there are other ways of tuning levers. For example, I would always say that use one tuning method at one go. Don't do all that at one instance only. The reason is if you have multiple tuning levers, then which tuning function is giving you the best result, you will miss out on that. Hence, go step by step. Once you know that based on your data, what is the best tuning levers, based on that, you invest or you spend time in terms of enhancing the accuracy. Okay, that is one of the better ways. Then tuning experiment, as I said, choose one lever at a time. Always have understanding of experience, determine set values for that, and run the experiment with the same data multiple times for better accuracy to get an optimization and compare and select the best option based on that. Don't combine anything on at first go. Always have multiple levers and then select the best option. Then things to remember is no one size fits for all. For example, for the iris data set, I got to know that through Colab that ReLU is the best and random normal is the best for the weights and biases. But that is not, you cannot generalize and say that this is the best for every data set. For example, in any face detection, the optimizer can change. The other optimizer can give you the better results. So based on that, you make a choice in terms of tuning the network. Okay. And the best value for hyperparameter depends on your specific use case and also input data. So please plan it. But I would say experiment to make sure that you understand how to tune the deep neural network. And first time will not give you the best result. So always try to have that in an independent data sets and try then whether it is real time or any of the data sets which you can get from Kaggle or GitHub. Okay, so hope today's class in terms of two real-time best examples One is real time, and the other one is on the using the Colab in terms of model optimization and tuning. Gave you some insights and also learning how to do that. If you need any of the samples or the data set or the program, feel free. I will leave this PPT as well as the data set and also programming Colab files with Shashank. You can collect it and practice for yourself for your learning purpose, as well as for if you want to use or take up deep neural network as your final project. Also, feel free to go ahead and do the tuning to better predict your results for your project or for your data set. So with that, if anyone has any questions, I'm happy to address in next 5 minutes. So and also I apologize for disconnect in between. So if you have any questions or anything, if you have a doubt in your mind, feel free to ask me now, or also you can connect me on LinkedIn for your questions or doubts or any mentoring or heads up or industry connects or even the best practice sharing. We will co-learn and we can co-create some of the best projects or best learning in the area of AI and ML for the better co-learning purposes. So that was about today's session.
Thank you, sir. Students, should you have questions, you can please ask or put it on the chat box. I'll give you about,
Yes.
we'll give you about 2 minutes.
Okay. So those who don't know me and want to connect, you can go to LinkedIn, search by Nandish, Nandish, Manangi. Get me, you can connect through this. Otherwise, also I will drop an email and phone number for your inquiry purpose.
Right. Thank you very much, sir. I'm not sure anybody has any questions, but I thank, first of all, the Department of Computer Science Engineering, AIML and Cybersecurity, and the Futurance Technologies for organizing the Industry Connect sessions every Saturday very religiously. We are, of course, very grateful to you, our resource person today, Dr. Nandish, for being a part of our Industry Connect session, especially on a Saturday evening like this. Thanks are due, of course, to my HOD, Dr. V. Vivek, the head of the Department of Computer Science Engineering in Artificial Intelligence and Machine Learning and Cybersecurity, and the entire team of faculty members for all their support they offer. Of course, thank you very much, students, for participating in this session. Please ensure that you fill up the survey link before you exit, and have a very happy weekend and good night.
Thank you, ma'am. Thank you so much.
Thank you.
And thank you, participant, for being a wonderful audience. Have a good rest of the evening.